So I'm going to show you guys how the um, KanrenReasoner, which is the new proposed inference engine for NARS, kind of how it's implemented, and just a little bit of a deeper dive into the mechanics of it. So let's start with like the high-level overview of what we're going to talk about. So in general, right, Narcisse is presented as a string. So for human output and just interoperability with other systems, for example. So we have something like this type of string, dog is an animal. Bowen already created a separate module that's part of PyNARS, but is can be extracted, and it's completely independent using grammar parsing, and it essentially converts between string and Narcisse back and forth, right? And here Narcisse I represented as a like pseudocode, but essentially it's just like different classes, like a statement, and it has some properties for subject, copula, predicate, and so on and so forth. So it's a module that can convert back and forth between the two. It is used, so the reasoner is going to depend on this Narcisse module, and the inputs into the Narcisse module are, well, into the reasoner module would be the, or inference engine more precisely, I guess. I should have written inference engine. So the Narcisse statements go in. We convert them to logic form internally. We'll talk about this in a little bit. And then once the conclusion is reached, we convert the logic form back into the Narcisse, and then it can be used throughout the rest of the system. So two main kind of like components are rules. How are rules defined? How are they kind of processed? And then how is the actual inference done? Right, so we'll start with the rules, and as you can see that, this is pretty much what you expect to find in a book. If we look at the Non-Axiomatic Logic book, that's more or less what they are defined as. So we have two premises, and then there's a conclusion and the truth function associated with this rule. So internally, as I said, we convert it to a logic form, and then there's also additional constraints that it's kind of implicit, but we're making them explicit that these terms should be distinct. And so let's see, right? Ideally, we would want to stick as close as possible to this type of form for readability, for just maintainability and other things. Because this is okay, but this reads better to a human eye, I think. So this is what the rules look like. It's a YAML file, so similar to like a JSON. It could be any one of those. Just I chose YAML just for its. I think it's very clean. So yeah, so you have this file which is loaded at initialization in the inference engine. And then this is what they're defined as. They're just strings. And we have the various levels of null. We have the immediate rules. We have the conditional compositional, null 5, null 3. So we have all of these rules here. And we also have theorems, which again define in a similar fashion, just like that, right? So we have quite a few, right? So if we think about it, there's quite a few different rules and theorems that we can apply. So, all right, let's go to what happens when we instantiate the inference engine. So as I said, we call this, we load up the rules from here. By the way, like if we wanted to disable the rules or something, there you go. So no more deduction. And then we call a couple of utility functions to split them up into separate lines, ignore the comments. That's what this function does. And then we iterate through the first two layers, replace the copulus to get the higher order statements. And then we also get the higher order rules, And then we also do the same for some of the now3 rules, and again, get the higher order versions of those. We put them all together, and then we store the results by calling those other utility functions you can see here that just call convert for the most part, right? So let's see what the convert does. So it just takes that line, for example, one of those, splits it up. That's just some string conversions to pick out the premises, the conclusion, and the rule. And then it calls parse, which that's actually the second portion that is here. It's calling the Narcisse layer, Narcisse module to just do the parsing for us, as we mentioned, right? So this is calling into this module right here. And so now that we've parsed it, we convert it to logic. So this is this step right here. Right, so we convert from this string form, which was then converted to Narcisse, which is now converted into logic. So the logic is right. So not too crazy, but and maybe it's overwhelming when you look at it. But if you read into it, you can see that it's just a bunch of if statements, more or less. If it's a statement, then you convert it to this const form with a copula first, and then the rest of the terms. If it's a compound, similar connector and a bunch of the terms, and we just call in the function recursively to build up the expression. And so this achieves this here, right here, from Narcisse to logic. And then for logic to Narcisse to go in the other direction, which we do here, like once we got the conclusion, we need to convert it back to Narcisse, so the rest of the application can use it. And so there's basically the opposite of that, opposite of the logic function that takes a logic form and then converts it back to Narcisse term. So here, it's pretty straightforward. Creates a statement, or creates a compound, or so on and so forth. So yeah, variables are a little trickier, but I can do a deeper dive if anybody is interested about how the variable elimination works, how the variable introduction, and like different other things here. So yeah, we're still here. We converted our things. So by calling this convert function, we got the logic form. This is, again, just something to do with the way the variables are handled. And these other ones, the convert immediate, they're same principle, just for like a single input instead of two or theorems, which again, they're a little special in how they work. But same pattern, as you can see, converting to logic and extracting some additional information. So now that we've loaded it up, and again, this happens only once during instantiation. So we don't convert back and forth all the time. It's just one time we take this representation that is convenient for humans to read and operate with, and we convert it into something that the logic engine can utilize. And now we're ready to move on to this step. So we have the rule table built up. We already know how to convert things. So somebody calls the inference function and passes us two statements that we need to see if there are any applicable rules in our, that match, and to derive the conclusions that are valid. So to do this, again, we call just the variable elimination. That's similar, just some housekeeping stuff. We convert the inputs, these guys, into logic versions. So we can see, right, we need them in the logic form. Could be cached on the terms themselves as a performance optimization, but again, that's details. And then we just iterate over all the rules, and we call apply. And if there is a result, then we calculate the truth function. So the truth functions, they are defined, so for each of these three-letter combinations that you find in the rules, the truth function is just mapped to a function elsewhere in the code. And yeah, we just append the results. And they apply this function. How is it done? This is where miniKanren comes in, because so far, up to this point, we haven't actually we utilized some of the data structures from miniKanren in order to convert to logic, but we haven't actually run anything. So this apply function is where most of the work happens. And the work is actually not that complex either. So we're just asking it to unify and produce a conclusion that unifies the premises and the rules given the constraints. So in this example, we have these are the two premises from the rule. This is the conclusion, and these are the constraints. And then here are the inputs that we were given, convert them to logic form. And so what this run does is, if there is a valid substitution that can be a substitution map that can be obtained, it'll return the results with the substitution. So in this case, right, we can match those T1 to P1 and P2 to T2 by this substitution map, where M is a dog, S is Sandy, P is animal. And then since it's valid, we can now produce the conclusion where Sandy is an animal. And that's exactly what this produces. Then we convert it back to the term, as you saw, right, like from logic form to the term, Narcisse term. And then this is a little detail I can explain later. And yeah, and immediate inference does the same thing, just one premise instead of two. And so structural is again similar, but it's going over the theorems, and then for each of the theorem it applies the rule. So and again, a little more housekeeping for handling theorems differently than syllogistic inference. And same for like compositional, again, same pattern, converting and iterating and call and apply, but again, some special stuff for handling variables. And that's all that I wanted to cover in this particular video. So yeah, hopefully you guys find this useful, and I'm looking forward to your feedback.